Good morning, everybody. It's my pleasure to moderate the first session. Just very briefly, I'd like to say that last year at the conference dinner, I made a challenge to Xavi, and Tim and Diana joined immediately to try to organize the CT here. Next day, Manuel was engaged already, and I'm very happy to see that you are happy and we are enjoying the city conference here. So I'd like to thank you really for accepting my challenge, and so that we are here in a category theory conference that I hope it will be very successful. So it's time to start, and I want to introduce the first speaker that everybody knows, Sandra Mantovani, who made me... Okay, her title is there. It's really a long title, Sandra. So we'll hear about Yoneda, additive regular spans, and cartesianmonoidal opfibrations.
Thank you very much, Manuel. So first of all, I would like to thank the scientific committee and the organizing committee for inviting me, and it's a great honor to open this session. And I'm very happy to be here. I was already here 35 years ago, and I was in the picture so many years ago, but it's really a pleasure to be here again in this wonderful city with this wonderful company. And I hope that everybody will enjoy this conference. So I will start this talk, and I will talk about this route towards two-dimensional, in the sense that we'll talk about two groups instead of groups. Cohomology, two groups instead cohomology groups, and this is the idea of two-dimensional cohomology groups. And the route is rather long. It starts in a very famous paper, Yoneda. It was 1960, and the idea was to look for exact sequences in an abelian category in order to define cohomology groups without having enough projective or injectors. And so you take a morphism of exact sequences, and what you do, the domain is the sequence E, and the codomain is the sequence E prime, and then we can define the category of extensions of length 2 in the category A. I will talk about length 2, but we can do the same for any length n, just to be in the easiest case, easiest just because it's not so long. But of course everything can be expressed also for different lengths. And we consider a functor which associate with any morphism of extensions two morphisms, a pair of morphism. The one alpha is between the co-kernels, while alpha beta is between the kernels. And then we have an object, a morphism of object in the product A squared. Of course, this S is given by two S0 and S1, and we can consider as a notation the extension starting from B and ending in A, and we say X square AB, which is exactly extensions we are given by S2. This notation is just to say that they end with A and starts with B. So S2 minus 1 AB. And the elements of the classical group X square AB are just the connected components of such a category. And what we can do, if we start with an extension and a morphism from A prime to A, we can pull this extension to another extension alpha star E with the same kernel. These, of course, are classical results in an abelian category. And this pulling back has a universal property. Because, of course, if we take another extension with the same, with the beta and the alpha prime between kernels and co-kernels, then if we have a morphism of exact sequences, then because of the properties of the pullback, of course, we can find exactly unique arrow inside the pullback. So thanks to this universal property of the pullback, we can show that S0 is a fibration, and each alpha admits an S1 vertical, because you see that we have the same kernels. So the extension we find pulling back P along alpha as the same kernel than the one we start with. And in a perfect dual way, we can start with a morphism, in this case covariant from B to B prime, using the push out, of course. We can obtain another extension with the same co-kernel. And in other words, we can prove in a dual way that S1 is a knot fibration. And each beta admits an S0 vertical co-Cartesian lift. Okay, what Yoneda did was to isolate the purely formal properties of this category of extensions of a given length and introduce a new notion. It was the notion of regular span. So what is a regular span? It's a span of categories such that S0 is a fibration with enough S1 vertical Cartesian liftings, and S1 dually is a knot fibration with enough S0 vertical co-Cartesian liftings. And this is not exactly what is known as a two-sided fibration, since a two-sided fibration is a regular span with a further condition. And we call it the condition C. If you start with a point, an element in X, and you take two morphisms, one from A to S0 X, and beta from S1 X B, then you find out an isomorphism between two objects, and these two objects are obtained by considering co-Cartesian followed by Cartesian, or the other way around. So in other words, if we start with such a situation, you have an object X, and you take a morphism in A and another in B, and then you can start by taking this lifting, okay, starting from X, and then this is you can choose for a vertical lifting, and then you can take the corresponding lifting on the other side over A, and this is a possible way to do that. But you could also start with a red arrow, which is again a vertical lifting, and then you go with beta at, but of course you are not sure that you can catch the same element. What you can do, of course, by the universal property of liftings, that you get an arrow, a canonical arrow omega. So the condition making a regular span with two-sided fibration is that such omega is an isomorphism. Okay, so what is the main result of the first part of this paper? just a modern version of this theorem that Yoneda called classification theorem. If you start with a regular span S, from X to A times B, then you can factorize such a span through a two-sided fibration S bar with discrete fibers. So a two-sided discrete fibration S bar. And you can get, of course, associated with this two-sided discrete vibration, a profunctor, or if you like, a functor from A up times B into Z. And the connected components of this functor are the elements of this S bar. Okay, so you start with S, and you consider the connected components of S, and you get a two-sided discrete vibration, of course, because they are sets. But what Yoneda was interested in was to endow these discrete fibers with an additive structure. So he introduced the notion of regular additive span. So easy, it's just the regular span where the three categories involved are additive categories. So X, A, and B, and S is an additive factor. So under such conditions, he proved the second theorem in his paper, and he called this additive classification theorem. So the factorization is the same, but starting from a regular additive span, the corresponding functor to the two-sided discrete vibration preserves finite products in each variables. Hence, thanks to this property, you can prove that for each pair of objects, A and B, the set S bar minus 1 AB inherits an abelian group structure. Moreover, if you fix any variable, you get functors S bar minus 1 with fixed A, and on the other side you fix B, factor through the category AB, the category of abelian groups, and then they are additive functors. So if you apply this result to the case of extensions, the above procedure gives a way to endow S2 AB with an abelian structure. And this structure is the so-called bar set. And this is the case of extension. This is the way we introduce the cohomology groups in the additive case. But we would like to treat in an analogous way also the case of cohomology of groups. And so we have to move into the context of cross-extension instead of just extension. And cohomology groups can be recovered in terms of cross-extensions. Is a known result. You fix a group with coefficients in a G module B. So you have an action of G over an abelian group B. So you take a crossed extension, which means that in the middle your partial is a cross module. And then you have a morphism of groups with an action of A1 over A2, and there are two axioms which are called which makes this partial a cross module. I don't have time to enter the details, but they are very known properties. And you consider a morphism as before between two cross extensions, which is given in the middle. You have a morphism of cross module. So these are equivariant morphisms. They take into account the action. And again, we can consider the category of crossed extensions of length 2. And we can do again, as in the abelian case, a procedure by taking pullbacks. So you start for in crossed extension E, you take a morphism over G, you pull it back, and again you get a crossed extension with the same kernel. And we get again that the functor that associate to any extension E, the first we have above, the co-kernel G, this pi 0 is a fibration. But we cannot use, as before, push out in order to have an opfibration. So what we can do is to fix a group G, and considering that we have a G module structure on B, we can construct co-Cartesian lifting only along G module morphisms with fixed G. Beta from a G module B, B phi, and B prime phi prime. And there is a construction which gives another extension along this G module morphism, beta lower star E, which has the same co-kernel. And so we can have again an opfibration, but just between fibers of the previous functor. So you have to fix the functor G. And you have this PG from those crossed extensions with fixed co-kernel G into the category of G modules, which associate with an extension the G module B. And this is an opfibration. Just a note, we can do again the same for crossed extension of any length, and maybe more important, we can work in a suitable semi-abelian context. Of course, you have to consider the suitable internal notion if you want to work in this intrinsic context of semi-abelian case. I don't have time to describe what semi-abelian categories are, but Marino after me will give us at least an idea of what is homological and in particular a semi-abelian category. But it's not so important in this at this moment. Okay, we have a problem because cross extensions of groups do not fit into Yoneda framework, and we don't have regular spans for two reasons. The first reason that our functors, initial functor, does not have a product as a codomain, and the other problem is that we don't have a global opfibration. So the problem is to find out a suitable framework in order to deal with non-additive cases, like the one of crossed extension. So, some years ago, together with, sorry, I forgot to say that this is a joint work with Alan Cigoli and Beppe Metere, and we work together also with Enrico Vitale with the first part of these results. And now we have to replace our regular span with a triangle. Instead of considering a single functor, we can consider this as a morphism between fibrations. Because pi 0 and u, the forgetful functor of any G module into G, the group, the acting group, and we have a morphism, a Cartesian functor is a morphism between fibrations. And if you look for the formal properties of the specific case, we can introduce this notion. It's very easy because, as happens in the case of crossed extension, we have a morphism of fibration, which is called a fiber-wise of fibration, since for any A in A, you can restrict P to the fibers, and then you get an operation, PA. And this is an easy generalization of a regular span because we have that a functor is a regular span, even though if it is a fiber-wise of fibration whose domain is the projection of a product. But we can have a generalization to this non-symmetric context of the notion of two-sided fibration. And in order to do that, we have to look to internal of fibration in the two categories of fibration over A. So, a morphism in the category of fibration over A is an internal of fibration in fib, even though it is a fiber-wide of fibration, but with a further condition. For each x in x, A in A, beta in M, with this property, because we have to stay into a fiber over this element, then we have an isomorphism, like an isomorphism as before. Just have a look. You see, is almost the same than before. You have again by playing with Cartesian lifting followed by Cartesian lifting and vice versa. The problem that in that case you have to lift to the fibers in order to perform Cartesian lifting, and anyway you can find again an omega between two objects in the category X. This is a canonical error thanks to the universal properties of Cartesian liftings and Cartesian liftings, and then you ask for this omega to be an iso as before. This is the condition C prime. They are summarized here. And this is another result by Bourne-Penon that you get a two-sided fibration even only if you have an internal fibration in the category of fibration over A, which has as codomain the projection of a product, exactly as in the case of regular span. Okay, in such a framework, we could provide a non-symmetric analog of Yoneda classification theory. Each fiber-wise of fibration, P, can be factorized in a universal way through a non-fibration, internal fibration in fib of A with discrete fibers. So you start with a P, which is a fiber-wise off-vibration, without fulfilling the condition C prime, and you get, again, by using the connected components, the fibers, you get an internal off-vibration with discrete fibers, which correspond to the case regular spine into two-sided discrete vibration. But it's a non-symmetric case. Okay, so back to the process extension. We apply this result to the case of xx squared, and x bar can be constructed as in the Milan case, in the same way, by taking as object the connected components of each fiber of the P. But again, we want to talk about cohomology, and then we want first to endow such fibers with an additive structure. Despite the fact that we are not, as before, in an additive asymmetric case, because X mod are not additive and U is not a product projection. However, something useful is again here. So if we consider the U fibers with fixed G, we have the category of G module, which is an abelian category. And restricting our P to the fibers over G, so the crossed extensions with co-kernel G and the category of G module, we have an off-vibration with discrete fibers. So associated with an off-vibration, of course, we have in this case, since it is discrete, a functor into set, and this is monoidal with regard to the Cartesian structures, which means, in other words, that it preserves finite products. And again, anytime you have a functor, a finite product preserving functor starting from an additive category, then you are sure that such a functor factorized through the category of abelian groups. And then, for each G module, B phi, we can obtain a group, which is, again, the group operation is again the Bayer sum, and this is isomorphic to the classical H3 cohomology groups with coefficients in the G module B. And this is the way of getting cohomology groups by using crossed extensions. But as I told you at the beginning, we would like to have something more, namely symmetric two groups instead of abelian groups. And recall that a symmetric two group is a symmetric monoidal groupoid where every object is sealed invertible, so invertible up to iso, with regard to the tensor product. And to understand how to perform, and if it is possible to have such a procedure, we need to analyze the properties of this last off-vibration before taking the connected components, so the original one, and of its corresponding pseudo-functor. Because this is an off-vibration and is no more discrete, and so you need to pseudo-functor instead of a functor associated with it. So we have a pseudo-functor from G mod into cut. And the second step, we need to find a different factorization of P through a suitable internal off-vibration P tilde with groupoidal fibers, because we want to have two groups structure over your fibers, and so you need groupoids, because any two group is, first of all, a groupoid. for the step 1. PG fibers, the one associated with the process extensions, are not group products. So what we can ask for is that our pseudo-functor factorizes through the two categories of symmetric monoidal categories and strong monoidal functors. So before looking for a factorization, a suitable factorization, what we can ask for is nothing more than this. And these two categories, symmetric monoidal categories, represent commutative pseudomonoids in the Cartesian two-category cat. So, what we are interested in are pseudo-functor start with the monoidal category, which are endowed with a lax monoidal structure. What is this? And why we are interested in such a pseudo-functor? Because we can rely on this result by Müller-Vasila-Coppola, Cristina, it was in 2020, and they found out that if you start with an opfibration between monoidal categories, then the corresponding pseudo-functor is equipped with the last monoidal structure, if and only if P is a strict monoidal functor, and the tensor product of co-Cartesian liftings, the tensor product of two co-Cartesian liftings is co-Cartesian. So tensor product preserves co-Cartesian liftings. And this is the general result. What happens? This is the reason why we are interested in such a contest to this spatial pseudo-functor, because the corresponding pseudo-functor, which is called monoidal, which is called lax monoidal, leads to a pseudo-functor between the pseudo-monoid structures. Which means that you can have a functor, a pseudo-functor, between the monoidal objects into B and the monoidal objects into cat, pseudo-monoidal objects into cat, which are exactly monoidal categories. But in particular, we are interested in cases where tensor product is nothing but the Cartesian product. So, Cartesian monoidal categories. So when both X and B are Cartesian, as the Cartesian product as monoidal structure, then P is called Cartesian monoidal fibration, and can be proved to be a Cartesian object in the two categories of the opfibration over cat. Just to recall that an object in a two category with finite products is Cartesian when the diagonal and the terminal arrows admit right adjoints. Okay. In a general two category. In the two category of opfibration, if you look for such conditions, you get exactly the Cartesian case of monoidal opfibrations. And this is an important point, because since our aim is to have groupoidal fibers eventually, if you look at the case of groupoidal fibers, so you start with an opfibration with groupoidal fiber with X and B, both Cartesian categories, and you look at the corresponding pseudo-functor, what you get that P is Cartesian monoidal, even only if P preserves finite products, in the sense that you should ask also for product binary product of co-Cartesian lattices are still co-Cartesian, but in this case, with groupoidal fibers, every morphism is co-Cartesian, so you don't need for the second condition. You just need preservation of finite products, and the corresponding pseudo-functor preserves again finite products, but up to pseudo-natural equivalences. So, starting with the Cartesian monoidal of fibration with B additive, we can conclude that corresponding pseudo-functor factorizes through symmetric monoidal categories because it is a corresponding pseudo-functor of a Cartesian monoidal of fibration, which means it's lax monoidal with respect to the Cartesian structure. Okay, and again, if we start with the Cartesian monoidal of fibration with codomain and additive category, then the associated pseudo-functor factors through symmetric to groups if and only if the fibers of P are groupoids. So the case of groupoidal fibers makes everything easier. So we can go back to process extensions, and it's easy to check that PG, so the opfibration you obtain by fixing the co-kernel of the extension, preserves finite products. And binary products of whole Cartesian map are still co-Cartesian. So this opfibration is actually a Cartesian monoidal opfibration. Exactly what we need. And just to mention, this result is very useful if you want to work in the intrinsic context of strongly semi-abelian categories. Was given by a paper of Diana Rodello, and it was based on properties of Bohr's direction factor. But in the case of groups, it's just a question of looking at the properties, and we can check it very easily. So, thanks to this result, we can say that for each G module, the fiber over this G module of the opfibration PG can be endowed with the symmetric monoidal structure. The problem is, can we put it all together? Which means, if we start with the fiber-wise opfibration, could we give it a convenient additional structure, as in the case of regular span, in order to get at least symmetric monoidal structure of the fiber, as in the case of process extensions? Okay, a first answer can be given if you start not just with a fiber-wise opfibration, but with an internal opfibration, like the one of process extension. Just to recall, this is the one with that conditional C prime. And in this case, we recover again Cartesian objects, and this P is called a fibred Cartesian monoidal fibration when it is a Cartesian object in the category of internal opfibration in the two category of fibration over rate. And of course, it's just a name, but this we have a characterization of such internal opfibration. So such a P is a fiber Cartesian monoidal opfibration if and only if the fibers of P0 and U have finite products and change of Bay functors preserve them. And more importantly, for each object A, the restriction PA, which is always an operation, in this case becomes a Cartesian monoidal operation. And then we can show that our P, the one we consider related to the process extension of groups, is a fiber Cartesian monoidal operation. But unfortunately, since we want to make a connection with regular additive span are not internal operation, and so we cannot use this result, the previous result. In general, they does not fulfill the condition 2. So the restrictions are not usually the Cartesian monoidal operation. So, in order to recapture regular additive span into our frame, we consider fiber-wise operation, which still fulfill the condition 1 of the previous characterization theorem, and another condition, 2 prime. You see that we ask for the restriction PA on the fibers to be an off-vibration with just preserved final products, without asking for the product of co-Cartesian maps to be still co-Cartesian. Something less. Again, if a fiber-wise off-vibration satisfies conditions 1 and 2 prime, and it has group fibers, then we can have what we need, so a fiber Cartesian monoidal operation. Once again, the importance of turning fibers into groupoids is highlighted also in this condition, and now relying on some results in these 2 papers of 2022 and 2023, we can perform this factorization, which is the main result I present today. So, if we start with the fiber-wise operation fib over A, which satisfies condition 1 and 2 prime, then by taking the category of fractions Q tilde of X with respect to P vertical morphisms, then we can obtain a fiber Cartesian monoidal operation P tilde, which has groupoidal fibers. So, the fact that we can obtain a P tilde with groupoidal fibers makes the, in some sense, easier to prove that this is a fiber Cartesian monoidal operation, which is what we need in order to perform this. Because if we restrict the attention to the case where the fibers of U are additive categories, exactly as in the case of process extensions, where the fibers are the category of G modules, then we can apply the previous result to P tilde, this new internal operation, and we can prove that for each object in M, the fiber P tilde minus 1 over M is a symmetric to groups, which means it can be endowed with a symmetric to group structure. And for each U vertical arrow from M to M prime, so if you take 2 objects of the same fiber over U, then the change of base functor is a symmetric monoidal functor, which respect this structure of 2 groups we have on both the fibers. So the last result applies, of course, since it was our starting idea, to the fiber Cartesian monoidal operation given by crossed extensions in groups. So if we apply these results, then we can define for each G module B a cohomology 2 groups. What that we studied in a paper on 2023. And what happens? First of all, this is a 2 group, so it has its homotopical invariance. The first one, which is pi 0, so if you take connected components of this 2 group H3, you can recover the usual cohomology group, H3. While, if you consider the second homotopy invariant, so the abelian group pi 1, which is given by the automorphism of the monoidal identity, then is shown to be isomorphic to H2, the second cohomology group. Which in turn, it appears also as a pi 0 of another 2 group. So, we can perform, we can apply our result also to this triangle, which is the triangle given by pi, starting from opx. Opx is the category of abelian extensions. So, in the case of groups, nothing but extensions with abelian kernel. And if you consider associated with any abelian extension the functor which assign to such an abelian extension the canonical G module structure of the abelian kernel B, you get a functor pi, which is again a internal operation in fib, and it is with groupoidal fibers. So you don't need to perform any factorization in this case. You get immediately that this pi is a fiber Cartesian monoidal opfibration with groupoidal fibers. And then you get what you need, so you can endow any fiber with a symmetric 2 group. And this will give you the symmetric 2 group H2, whose pi 0 is exactly, again, the usual cohomology group. So this H2 plays 2 roles, is a pi 1 of the H3 2 group, and is a pi 0 of the lower group H2. Okay, so ready to go back to regular additive spans. Okay, first of all we have to show that regular additive spans can fit inside our framework, and then we want to show that they fulfill condition 1 and 2, and for this we need this proposition which gives sufficient conditions that are very easy to be checked. So if you start with the fiber-wise opfibration, and you assume that you have finite products, and that P and U preserve them, just preservation of fiber products, then P satisfies condition 1 and 2 prime. So that you can apply to this condition our main theorem. And it's very easy, of course, to show that a regular additive span, since it is an additive functors between additive categories, it preserves finite products. And then you can apply our main theorem to the case of regular additive span. We factorize this regular additive span through the category fraction of x with respect to the s vertical morphism. Then we get a two-sided fibration, which is now not discrete, but with groupoidal fibers, whose associated pseudo-functor preserve finite products, of course not up to iso, but up to pseudo-equivalencies, pseudo-natural equivalencies. And then we can endow every fiber, which is of course a groupoid, with a symmetric two structure, and the pseudo-functors you obtain by fixing each variable, then factor through symmetric two groups. So obtaining this one-up dimension with respect to the additive classification theory of Yoneda. Okay, so that's it. Thank you so much for the attention.
Thank you, Sandra. Are there questions or comments? Yes, go on.
The fact that you replace fibers by their connected components is reminiscent of the monotone light factorization topology. Is there a categorical explanation?
Actually, if this is a factorization, which is the co-comprehensive factorization, which is given by this, you can obtain discrete opfibration, and so you have this co-comprehensive factorization in the category of vibration over A. So it's related to a genuine factorization system in the category.
Richard?
Thanks for the talk, that was really nice.
Thank you.
So, this is a sort of very vague question, but so you construct this cohomology 2-group, 8-group. Now, those can be presented by some kind of very small set of data, right? There's an abelian group and there's a group of some combination.
Yes.
So, I was wondering if you could look back at this crossed extensions over G into G mod before you take the...
The connected component.
Before you invert the fibers. So then, is there some sense in which you could see that as somehow presented by some basic data? Is it sort of generated in some way? Or is that...
You mean what you have, of course, is just a symmetric monoidal cat in that case before performing the factorization. And of course, I mean, I don't know which is this, maybe this paper, the third cohomology 2 group, we describe what you get exactly when you are performing the category of fractions. And this you can understand how you change just morphism between crossed extension, between weak maps, which are described by butterflies. And then, by using these weak maps, you can have also the inverse. Of course, you have to take the classifying category because you have a bi-category, and then you can perform the biasum also in this context that, in some sense, derive from the spatial weak maps given by the morphisms, but you have to turn into weak maps instead of having, in order to perform the inverse, of course. But the product became almost the same, I would say. But you have to perform the inverse, the pseudo inverse. I don't know if I answered to your question, but maybe we described this third cohomology group in details in that paper. So I have no time to describe now, but there's a very detailed description. Maybe you can find an answer there.
Are there any more questions or comments? Yeah, sorry.
Very quickly. All these holes in semi-ring paragraphs? Or what's the context?
I mean, I think so, but what we propose is in a strongly semi-ring. Yeah. Just because, you know, we use, it's much easier to use the Smith-Isou condition.
And David? Yeah.
Thanks, this is a very nice talk. I know of an obstruction in H3 to the existence of extensions in H2, at least just in the group case, I don't know about the module case. And I was wondering if you could see that appearing here, in your grouplet stories, that are very nice, concrete obstruction to the existence of sections that lives in H3.
Sorry, I can hear your question.
I know of an obstruction to the existence of extensions in H2 that lives in H3, at least in the non-twisted case. I don't know about the modules. So I was wondering if there's a nice story where that would appear in your groupoid, your two-group story, that when it vanishes, you know that you have at least some extensions.
I don't know. I don't know. I should think a little bit about that.
Walter?
Yeah, I don't have a question, just a general remark. I'm very pleased to see how you celebrated Yoneda's work. You use the Yoneda lemma all the time, but many people haven't read this. But implicitly, I think you also celebrated Roderick and Denabou, because if you look at MacLean's book, even in the second edition, you don't see the word fibration. And this is just a notion that has been undervalued in category theory by many people for a long time. So we see a reversal of this. I'm glad to see that too.
I realize that. No, I mean, I take a lot, but thank you, Martin.
Okay, so let's thank the speaker again.